So we talked about functions, talked about constraints, and for some reasons, we need to tell you there are two kinds of constraints. They are sign constraints and they are functional constraints. Basically, if you have a constraint saying that there is a single variable which should be non-negative or which should be non-positive, you are talking about the sign of a specific variable. In that case, we say this is a sign constraint. Okay, we will very quickly see why we want to separate them. So if you have any function where the right hand side value is not 0, or the left hand side combination of variables is not just a single one, then that's the other cases. We say this is a functional constraint. So when you look at the constraint, either it is a sign constraint or it is a functional constraint. When you are having some sign constraints, if your x cannot be negative, we say it is a non-negative variable. If it is the case that it cannot be greater than 0, we say it is non-positive. If your x has no sign constraint, we say it is unrestricted in sign. Okay, so abbreviated as URS dot. Or we say it is free. That basically means there's no restriction on its sign. Okay, so it may be positive, it may be negative, it may be 0. It's only restricted by other functional constraints. So if we have constraints, very quickly we may talk about feasible solution. Any value combination of all your decision variable form a solution, but some are feasible, some are not. A feasible solution satisfies all the constraints, so it is an executable plan. Alright? On the other hand, if you have a solution that violates at least one constraint, it is an infeasible solution. It's still called a solution, but it is infeasible. So an example is here. We have 3 functional constraints and 2 sign constraints, and we have several candidate solutions. So for example, x1, which is 2, 3. If you plug in 2, 3 into these functions, you may see that 2 is less than or equal to 10. This is fine. 2 plus 2 times 6 for this particular, times 3. In this particular case, it is still feasible. For the last one, 2 minus 2 times 3. This is still, again, feasible. So basically, we can say that the solution x1 is a feasible solution. Because if you plug in 2, 3 into this particular set of constraints, it satisfies everything. Okay. And very quickly, you may check the other candidate solutions. For example, x3. x3 is 6, 6, and you may very quickly see that it violates the second constraint, right? Because 6 plus 12 is greater than or equal to 12, is greater than 12. So this is not allowed. This guy is infeasible. Okay? So combining all those feasible solutions, we get a feasible region, or sometimes we call it a feasible set. Of course, it may be empty. If you have a random, if you have any specific mathematical program, it's always possible that some constraints are conflicting with each other, and there is no way to satisfy all constraints at the same time. In that case, you don't have any feasible solution, and your feasible region is empty. Inside the set of all the feasible solutions, we want to look for an optimal solution. Pretty much that's the meaning for solving a program. Okay? So an optimal solution is a feasible solution that is optimal, that is the best. So technically it means if you are talking about a maximization problem, then that feasible solution gives you the largest possible objective value. If this is a minimization problem, that feasible solution gives you the smallest possible objective value. Or intuitively, when you say one thing is optimal, there is no feasible thing that can be even better than that. Here, when we say better, we mean strictly better. Okay, so they cannot have a tie. They cannot be equally good. When you say one thing is optimal, and if I want to challenge you, I want to say, no, you're wrong. I need to give you a solution, a feasible solution that is strictly better. Then I can say your solution is not optimal. So that somehow suggests you one fact. An optimal solution may actually be unique or not unique. So sometimes we have a linear program with multiple optimal solutions. That's possible. Or it's also possible that there is no optimal solution at all. For example, if your feasible region is empty, you don't have any feasible solution, then you don't have any optimal solution. Or it's also possible that you have a mathematical program. There are feasible solutions, but there is no optimal solution. Very quickly, we will show you why it is possible. Next, we need to talk about very important concept, which is called binding constraints. So it is a property for constraint when you are talking about a specific solution. So let's take a look at this definition. Suppose we have G of something less than or equal to B as an inequality constraint, and X bar is a specific solution. Then this particular inequality constraint is said to be binding at X. Okay, so it's binding at X bar if when you plug in X bar, you get an equality constraint. Okay, so pretty much that says when you have an inequality constraint and there is a solution, once you plug in, that becomes equality. If that's the case, then we say this constraint is binding at X bar. So an inequality, of course, may also be non-binding at a point, at a solution, if it is strict instead of equality at that point. If you plug in and you see there is indeed a positive gap between the two sides, then that inequality is non-binding. So if you have that definition and you look back at an equality constraint, if you have a feasible solution, it must be some kind of binding thing happening on that inequality, right? Any equality constraint must be binding at any feasible solution, because if you plug in, that becomes an equality. So here are some numerical examples. I have an inequality constraint which is x1 plus x2 less than or equal to 10. This constraint is binding at 2, 8. Because if you plug in 2, 8, that becomes an equality. On the contrary, this constraint 2x1 plus x2 greater than or equal to 6, this is non-binding at 2, 8. Because once you plug in 2, 8, you may see the left-hand side is strictly better than, strictly greater than the right-hand side. This means the constraint is non-binding. The last one is an equality constraint. As this is a feasible solution, you plug in, you get equality. Again, this is binding. So the definition of binding constraint applies to both inequality and equality constraints. But typically, we focus more on inequality constraints when we are talking about binding or not, because we basically always care about feasible solution, and then equality constraint is always binding at any feasible solution. Okay, so intuitively or geometrically, if you have a constraint saying that your feasible region is this part, then this point, if a point lies at the boundary, then you know this constraint is binding at that point. If another point lies in the interior of that feasible region, then you know this constraint is not binding at that interior point. Okay? Lastly, binding, non-binding are sometimes called active, inactive constraints by some other scholars. So they are pretty much the same thing. Whether a constraint is binding at one point basically means whether a constraint is active at that point. So we mentioned about inequalities, and we all know that an inequality may be strict or weak. So you may have a strict inequality or a weak inequality. A strict inequality means the two sides cannot be equal, like x1 plus x2 should be greater than 5. If that's the case, then 2, 3 does not satisfy this inequality because 2 plus 3 equals 5. This is not allowed. It is an weak inequality if the two sides are allowed to be equal. Okay, so the thing that we want to remind you is that in mathematics, both are possible. But in OR, if we are talking about practical applications, inequalities are always weak. Okay, we only work on weak inequalities in this course. Why is that? Because with strict inequality, sometimes an optimal solution actually does not exist, which is very weird, I would say. So for example, there is a very simple formulation here. There is a real line. I want to try to push x to the left as small as possible. But there is a constraint saying that your x must be greater than 0. So in that case, you don't have optimal solution, right? If you say 0.1 is optimal, I give you 0.01. If you say 0.01 is optimal, I give you 0.001. You also cannot say that 0 is optimal because 0 is not feasible. So if we allow strict inequalities, the feasible set, technically may not be closed. Okay, you would see some boundaries that you cannot reach, and that may result in the case that your optimal solution, does not exist. So mathematically, it's weird enough. Practically, it can be even more weird because practically, in most cases, the constraints by nature are weak. Why is that? Think about your budget constraints. Suppose you have $500. You want to use that $500 to buy several things. So that's a decision problem, right? So that typically means you cannot spend more than 500. So 501 not allowed. 550 cents not allowed. But you are allowed to spend exactly 500, right? So I hope this small example shows you or convince you that in practice, most of the decision problems face inequality constraints, and we face weak inequality constraints. When you have budget constraints, you are allowed to spend all your budget. When you have capacity constraints, you are allowed to use all your capacities. When you have demand fulfillment constraints, you are allowed to just meet the demand. So we will always focus on weak inequalities in the whole course.